Today we are going to discuss chemical reactions. Since aldehyde and ketone both possess carbonyl functional group, they undergo similar chemical reactions. First type of reaction is nucleophilic addition reactions. Contrary to electrophilic addition reactions observed in alkene, the aldehyde and ketone undergo nucleophilic addition reactions. Here is the mechanism of nucleophilic addition reaction. A nucleophile attacks the electrophilic carbon atom of the polar carbonyl group from a direction approximately perpendicular to the plane of sp2 hybridized orbital of carbonyl carbon, as it is shown in figure 8.2. So let's try to understand the mechanism. Here this is the carbonyl carbon bonded to oxygen with a double bond. So this carbon is carbonyl carbon. Oxygen is more electronegative than carbon. So here the dipole will be shifted towards oxygen. As the dipole shifted towards oxygen, oxygen will develop delta negative charge and carbon will develop delta positive. So this positively charged carbon is the electrophilic center, as this carbon is electron deficient. This carbon is electron deficient. As it is electron deficient, you can call it electrophilic carbon. So this is electrophilic carbon. As this carbon is electrophilic, the attacking reagent will be the nucleophile. Now find out the hybridization of this carbonyl carbon. As this carbonyl carbon has made 3 sigma bonds and 1 pi bond. For the formation of 3 sigma bond, the hybridization will be sp2 and the geometry for sp2 hybridized carbon is trigonal planar. So that's why it is written here, the nucleophile attacks the electrophilic carbon perpendicular to the plane of sp2 hybridized orbital of carbonyl carbon. The hybridization of carbon changes from sp2 to sp3 in this process. So now let's see the mechanism of the reaction. So this is the carbonyl carbon and here there are 2 valencies of carbon. When attacking reagent nucleophile approaches to carbonyl carbon, it will attack to electron deficient carbon and this pi bond moves to oxygen. As a result of it, this sp2 hybridized carbon changes to sp3 hybridized carbon, as this is a nucleophilic addition reaction. So here this carbon and here this is oxygen. When pi electrons move to oxygen, oxygen becomes negatively charged and here there are 2 valencies and here this is nucleophile which has made bond with the carbon. So this carbon has made 4 sigma bond. For the formation of 4 sigma bonds, hybridization will be sp3. Previously it has made 3 sigma bonds. That's why hybridization of the carbonyl carbon was sp2. So let's read from the book. The hybridization of carbon changes from sp2 to sp3 in this process and tetrahedral alkoxide intermediate is produced. So here this intermediate which is produced, this is alkoxide. This is alkoxide intermediate. Now let's read from the book. This intermediate captures a proton from the reaction medium. So this intermediate captures a proton from the reaction medium to give electrically neutral product. So what will happen when it captures proton from the reaction medium? So here it will capture proton from the reaction medium and as a result of it, this negatively charged oxygen will capture proton from the reaction medium and here there was nucleophile. So now this is the electrically neutral product. Now come to the reactivity. Aldehydes are generally more reactive than ketone in nucleophilic addition reaction due to steric and electronic reasons. So there are 2 reasons. One is steric and the other one is electronic. So let's read the steric reason. Sterically, the presence of 2 relatively large substituents in ketone hinders the approach of nucleophile to the carbonyl carbon than an aldehyde, having only one such substituent. So let's try to understand the steric reason. So here it is written that aldehydes aldehydes are more reactive than ketone. So now draw the structure of aldehyde. So this is carbonyl carbon, and to one side it is bonded to hydrogen, and on the other side it is bonded to alkyl group. And here this is ketone. To both sides it is bonded to alkyl group. So because of the presence of these two bulky R groups, it is sterically hindered. So when nucleophile try to approach to carbonyl carbon, these two alkyl groups hinders the path of nucleophile. That's why ketones are less reactive. While in case of aldehyde, there is only one alkyl group. So that's why it doesn't hinder the path of nucleophile. So this was the steric reason for the lower reactivity of ketone or the higher reactivity of aldehyde. Now come to the electronic reason. So let's read from the book. Electronically, aldehydes are more reactive than ketones because two alkyl groups reduce the electrophilicity of carbonyl carbon more effectively than in former. In case of ketone, there are two alkyl groups which donate electron density to carbonyl carbon via plus I effect. So there are two plus I effects. By the donation of electron density to carbonyl carbon, the delta positive charge over carbon reduces. So that's why the carbonyl carbon become less electron deficient. While in case of aldehyde, there is only one alkyl group which donate electron density to carbonyl carbon. So that's why the carbonyl carbon in case of aldehyde, this is more electron deficient. As the carbonyl carbon in aldehyde is more electron deficient, it will undergo faster nucleophilic addition reaction as compared to ketone. Now come to the example 8.3. Would you expect benzaldehyde to be more reactive or less reactive in nucleophilic addition reaction than propanol? So here you have to compare between the benzaldehyde and propanol. So let's try to find out the answer of this question. First of all, draw the structure of propanol. This is CH3, CH2, C, double bond O, and here this is H. So this is propanol. Now draw the structure for benzaldehyde. So this is benzene, to which aldehyde functional group is bonded. So here this is benzaldehyde. Here this is one alkyl group which donate electron density through plus I effect to carbonyl carbon. So this carbon is the electron deficient carbon. But in case of benzaldehyde, and here there is resonance. Pi electrons of benzene ring contributes in the resonance of benzaldehyde, and because of it you will get another resonating structure. In this resonating structure, when you see here, this is the carbon and it is doubly bonded to benzene. This is hydrogen, here O negative. Here the oxygen is negatively charged, and this negatively charged oxygen cannot withdraw electron density as strongly as it withdraw electron density in case of carbonyl carbon. So that's why this carbon is less electron deficient as compared to the carbon of propanol. That's why propanol will be more reactive. The carbon atom of carbonyl group of benzaldehyde is less electrophilic than the carbon atom of carbonyl group present in propanol. The polarity of carbonyl group is reduced in benzaldehyde due to resonance as shown below, hence it is less reactive than propanol. Now come to some important examples of nucleophilic addition and nucleophilic addition elimination reactions. Here the first reaction is the addition of hydrogen cyanide. Aldehyde and ketones react with hydrogen cyanide to yield cyanohydrin. The reaction occurs very slowly with pure HCN. Therefore, it is catalyzed by a base and generated cyanide ion. Being a strong nucleophile, readily adds to the carbonyl group to yield corresponding cyanohydrin. Cyanohydrins are useful synthetic intermediate. So let's try to understand the reaction. So here we are going to discuss the addition of HCN. So here we are going to discuss the addition of HCN. For the addition of HCN, you have to take base. So this is HCN. When it reacts with base or you can say OH negative ions are there. So these OH negative ion abstract H plus from the HCN, and as a result of it, it produces water and Cn negative ion. And this Cn negative ion acts as a nucleophile for this reaction. So this is the nucleophile of this reaction. Now let's add this nucleophile to the carbonyl carbon. So this is the carbonyl carbon. In this carbonyl carbon, carbon is electron deficient and oxygen is electron rich. So the nucleophile, which is a cyanide ion, Cn negative ion. So this nucleophile, which is a cyanide ion, will attack on carbonyl carbon and the pi bond move to oxygen. So here you will get, this is carbonyl carbon. Now this carbonyl carbon become tetrahedral. Now cyanide will get attached to carbonyl carbon. So here this is cyanide, and on the other side oxygen, this oxygen will develop negative charge because the pi bonds are moved to oxygen. So this oxygen become negatively charged. Now this negatively charged oxygen will abstract proton from the reaction medium. So this oxygen will abstract proton from the reaction medium, and here you will get, here cyanide is already bonded to carbonyl carbon, and this oxygen will abstract proton from the reaction medium. So here it will become OH. So in this product, cyanide and hydroxyl, both the groups are there. That's why it is called as cyanohydrin. Hydrin stands for OH and cyano is for Cn. So the name of this product is cyanohydrin. So this cyanohydrin is a useful intermediate. When it undergo oxidation, cyanide group converts into carboxylic group. When it undergo reduction, cyanide group converts into primary amine. So that's why the cyanohydrin is a useful intermediate. Now come to the next reaction, addition of sodium hydrogen sulphite. Sodium hydrogen sulphite adds to aldehyde and ketone to form addition product. So here NaHSO3 is sodium hydrogen sulphite. To understand the nucleophile of this reaction, first of all you have to draw the structure of sodium hydrogen sulphite. Now let's draw the structure of sodium hydrogen sulphite. So here this is the structure of sodium hydrogen sulphite. This O negative ion, it get combined with Na positive ion. So this is the structure of sodium hydrogen sulphite. So here this is the nucleophile. And this nucleophile is O SO2H, and here oxygen carries negative charge. Means bond is formed by a oxygen. Now draw the structure of carbonyl carbon. So this is carbonyl carbon. When it reacts with sodium hydrogen sulphite, now you know what is the nucleophile. Nucleophile is O SO2H negative ion. So this O negative ion will attack on carbonyl carbon and make a bond with it, and the pi bond move to oxygen. Now draw the structure of intermediate. So here this is the carbonyl carbon. Now it become tetrahedral. So here O SO2H will get attached and oxygen will become O negative. Now this tetrahedral intermediate will abstract proton from the reaction medium. After abstraction of proton from the reaction medium, here you will get this is OSO2H and this oxygen will become OH, hydroxyl. So this is the product of this reaction. This is bisulfite addition compound and this is crystalline in nature. So let's read from the book. The sodium hydrogen sulfite adds to aldehyde and ketone to form addition product. The position of the equilibrium lies largely to the right side for most aldehyde and left side for the most ketone due to steric reason. Means here also aldehyde reacts faster as compared to ketone. The hydrogen sulfide addition compound is water soluble and they can be converted back to the original carbonyl compound by treating it with dilute mineral acid or alkali. Means the reaction is reversible. You can get back the carbonyl compound by addition of dilute acid or base. Therefore, these are useful for the separation and purification of aldehyde. Because the formed bisulfite product is crystalline, so they can be separated in the form of addition product, and when you add dilute acid or base to the reaction medium, you will get back your carbonyl compound, which can be aldehyde or the ketone. Now come to the addition of Grignard reagent that you have learned in the previous chapter. But still we can revise the addition of Grignard reagent. So this is carbonyl carbon and when it react with R, MgX. Magnesium is electropositive element, so the alkyl group will develop negative charge. So in case of Grignard reagent, R negative ion is the nucleophile of this reaction. And when it attack on the carbonyl carbon, pi bond move to oxygen and here you will get C, single bond oxygen. It has developed negative charge and on the other side R, and these are the two valencies of carbonyl group. So after the workup, here water, you will get C OH and here this is R and this. So by the addition of Grignard reagent to carbonyl carbon, you will get alcohol. This alcohol may be primary, secondary or tertiary depending on the carbonyl group, whether it is formaldehyde, aldehyde or ketone. We have discussed this reaction in detail in the previous chapter. Now come to the addition of alcohol. Aldehyde react with one equivalent of monohydric alcohol in presence of dry hydrogen chloride to yield alkoxy alcohol intermediate known as hemiacetal, which further react with one more molecule of alcohol to give gem dialkoxy compound known as acetal, as shown in the reaction. Here this is aldehyde when it react with alcohol in presence of HCl gas. This alkoxy alcohol intermediate is formed. This is called alkoxy alcohol. Because of the presence of alkoxy group, OR is the alkoxy group and here alcohol functional group is also there. So this intermediate is called hemiacetal, which on further react with another molecule of alcohol and it gives gem dialkoxy compound. This is called as acetal. Now let's try to understand the reaction mechanism for this reaction. Here this is aldehyde R, C double bond O, H. This is aldehyde and when it react with ROH. In alcohol, oxygen has two lone pair of electrons. As this is a neutral molecule, it is a weak nucleophile. So it is a weak nucleophile. So that's why to fasten the reaction or to make the reaction possible, acidic medium is taken in the form of dry HCl. So for this reaction, catalyst is required and here the catalyst is dry HCl gas. Now let's try to understand the reaction mechanism. So this is R C double bond O H. When it reacts with HCl, oxygen has lone pair of electron. So this oxygen abstract proton from HCl. So here you will get R C double bond O, and as this oxygen abstract proton from the HCl molecule, this oxygen develops positive charge. And here there was hydrogen. To neutralize this positive charge, double bond moves to oxygen, and as a result of it, R C single bond OH, and here there was hydrogen. This carbon develops positive charge. As the double bond moves to oxygen, this carbonyl carbon develops positive charge. Now this electrophilic carbonyl carbon react with the alcohol molecule. So here this is R O H. There are two lone pair of electrons. So now this alcohol molecule attack on this positively charged carbon. So here you will get R C OH. There was hydrogen. So as the oxygen of alcohol make a bond with the carbonyl carbon, here you will get O. One side it is bonded to H, on the other side it is bonded to R. As this oxygen donated lone pair of electron to carbocation, this oxygen develops positive charge. To neutralize the positive charge over oxygen, this hydrogen leaves the molecule in the form of H plus ion. So here you will get C, it is bonded to R, and here there was OH, here it is bonded to H, and now here it is bonded to OR. So this is the hemiacetal. Hemiacetal, this is alkoxy alcohol. Alkoxy alcohol. So this is unstable intermediate. So now it will react with the another molecule of alcohol, ROH, in presence of HCl. Again the oxygen of OH will abstract proton from HCl. So as it abstract proton from HCl, it will form RCOH2. Now this oxygen develops positive charge, as it has donated lone pair of electron to H plus ion. Here it was H, and here it is bonded to OR. As this alcohol has lone pair of electron, it will attack on the carbon and expel OH2 positive in the form of neutral water molecule. So here you will get the product RC. Water is removed from the molecule and alcohol will get attached to this. So here this is ROH. Here there was hydrogen, and here there was OH. As oxygen donated a pair of electron to carbon, this oxygen is positively charged. Now to neutralize this positive charge over oxygen, hydrogen leaves the molecule in the form of H plus ion. So here you will get RCOR. Here there was H, and here there was OR. So now this is the gem dialkoxy compound, and this is called as acetal. Now let's read from the book. Ketone react with ethylene glycol under the similar condition to forms cyclic product known as ethylene glycol ketones. Now let's try to understand the reaction as it is given here. This is ketone when it react with ethylene glycol in presence of HCl gas. It gives cyclic ketone and water is removed as a byproduct. Now let's try to understand the reaction mechanism of this reaction. So let's draw ketone molecule. This is carbonyl carbon and it is bonded to two sides with the alkyl groups. In presence of HCl, In presence of HCl, oxygen gets protonated. So here you will get C double bond OH. As this oxygen donated a pair of electron to H plus, it will develop positive charge. And here it was already bonded to two alkyl groups. To neutralize this positive charge, pi bond moves to oxygen. So here you will get carbon, here it is OH, and here it was bonded to two alkyl groups. As the pi bond moves to oxygen, carbon develops positive charge. Now this positively charged carbon reacts with ethylene glycol. So here let's draw the structure of ethylene glycol. So here this is OH. It is bonded to CH2, OH. Now one of the oxygen get attached to positively charged carbon. So here you will get carbon. There were two alkyl groups. And here there was OH. Now this oxygen make bond with the carbon. So here this is oxygen. It was bonded to hydrogen. On the other side it was bonded to CH2, and here it was OH. Now this oxygen develops positive charge. To neutralize this positive charge, this hydrogen leaves the molecule in the form of H plus ion. So here you will get C. There are two alkyl groups. Here it was OH, and here O. It is bonded to CH2. Here it is CH2, and here it is bonded to OH. Now again in the presence of HCl gas. So here it was HCl gas. So this OH will abstract proton from the HCl. Here you will get C, R group, and here it was OH2 positive, and here it was bonded to O, CH2, OH. Now these lone pair of oxygen attack on the carbon and expel this as a water molecule. So here you will get C. There were two alkyl groups, and here this OH will get attached to the carbon. So here it was CH2. Here there was oxygen which was bonded to carbon. As this oxygen donated a pair of electron to carbon, this oxygen develops positive charge. Now to neutralize the charge over oxygen, this hydrogen leaves the molecule in the form of H plus ion. So here you will get the final product. This is carbon. It was bonded to two alkyl groups, and here it is oxygen bonded to CH2, oxygen, and it is bonded to CH2. So this is the cyclic ketal. As it is formed by the ketone, the name is ketal. When it was formed with the aldehyde, the name was acetal. So this is the only difference between ketal and acetal. Now let's read from the book. Dry hydrogen chloride protonates the oxygen of carbonyl compound and therefore increases the electrophilicity of the carbonyl carbon, facilitating the nucleophilic attack of ethylene glycol. Acetal and ketals are hydrolyzed with aqueous mineral acid to yield the corresponding aldehyde and ketone respectively. Means these reactions are reversible. So when they are treated with dilute mineral acid. So when the cyclic ketal treated with dilute HCl, it gives back the ketone and ethylene glycol. Similarly, in case of acetal, when it is treated with the dilute mineral acid, it gives the aldehyde and alcohol back. Now come to the next reaction, the addition of ammonia and its derivative. Nucleophiles such as ammonia and its derivative NH2Z add to the carbonyl group of aldehyde and ketone. The reaction is reversible and catalyzed by acid. The equilibrium favors the product formation due to the rapid dehydration of the intermediate to form C double bond NZ. Now let's try to understand the reaction mechanism of this reaction. As we have added alcohol to carbonyl carbon, similarly you can add ammonia or ammonia derivative to the carbonyl carbon. So this is the carbonyl carbon and the reaction is catalyzed by the acid, means in presence of H+. So when H+ is present in the reaction medium, this oxygen gets protonated. So it will make bond with the H+ ion. So here you will get C double bond O. As it has donated a pair of electron to H+, it will develop positive charge. And here you will get H. Now to neutralize the charge over oxygen, pi electrons move to oxygen. And as a result of it, this carbon develops positive charge. So here it was OH and there were two valencies of carbon, and now this carbon become positively charged. So this electrophilic carbon undergo nucleophilic addition reaction. So here when it react with H, N, H, and there is some Z group bonded to nitrogen. Nitrogen has a pair of electron, so it will attack on this positively charged carbon. When it attack on the positively charged carbon, here you will get carbon and there was OH and there were two free valencies. Now this nitrogen has made bond with the carbon and there was two other hydrogens and it was already bonded to Z group. So as this nitrogen donated a pair of electron to carbon, now this can become positively charged. And to neutralize the charge over nitrogen, one of the hydrogen leave the molecule in the form of H+ ion. So here you will get carbon, there was OH, there were two free valencies. Now this is nitrogen. It is bonded to one of the hydrogen and here it was bonded to Z group. Now again this OH will get protonate in presence of H+. So here there H+, and now this oxygen get protonated. It will abstract H+ from the reaction medium. So here you will get carbon and here OH2. Now this oxygen develops positive charge. And there were two free valencies and there was N. It was bonded to H and there is one Z group. To facilitate the removal of water molecule, the bond between nitrogen and hydrogen move between carbon and nitrogen, and that's how it expel the water molecule from this intermediate. So here you will get carbon. Now double bond is formed between nitrogen and carbon and it was bonded to Z group. So that's how you will get this product, and water is removed as a byproduct. Now let's examine the table 8.2. Here there are different Z groups. If the Z is equal to H, means it was ammonia. When the carbonyl compound react with ammonia, here you will get C double bond NH, and this is called as imine. So there is a short trick to get the product of this reaction. You just have to remove water molecules. So this is the carbonyl carbon. When it react with H2N single bond Z. So here we have changed the value of Z. If the value of Z is equal to H, means you have to react the carbonyl carbon with the H2NH. So this is nothing but the ammonia. So here remove the water molecule. So here O is removed from the carbonyl carbon and H2 is removed from the ammonia. So here you will get carbon. There were two free valencies and it is bonded to double bond NH. So this is called as imine. This is imine. Now When it react with amine, again write the reaction with the carbonyl carbon and amine. So here this is the carbonyl carbon, and when it react with amine, amine means RNH2. So here you have to write it in the reverse order. So when you write it in the reverse order, you will get H2, N and R, means Z is the R group. Here Z is the R group. Now remove the water molecule. So hydrogen H2 is removed from the amine and oxygen is removed from the carbonyl carbon. So here you will get the product. This is carbon double bond. Here you will get N single bond R. So this is called as substituted imine or the Schiff base. Now if the Z group is OH, now write the reaction. Here this is C double bond O. When it react with hydroxylamine, hydroxylamine means here this is H2N and the Z group is OH. This is hydroxylamine. Hydroxylamine. So again remove the water molecule. So here when you remove this water molecule, you will get the product carbon double bond. Here you will get NOH. This is oxime. Now write the next reaction when the Z group is NH2. So here this is carbonyl carbon. When it react with NH2 NH2, so it H2N and Z is again NH2. So this is hydrazine. When it react with hydrazine, again remove the water molecule. So water is removed from like this. So here you will get C double bond. Here you will get N single bond NH2. This is called as hydrazone. This is hydrazone and it was hydrazine. Now come to the next reaction. When the Z is NH attached to phenyl group, means the reagent is phenylhydrazine. Here write the reaction. This is the carbonyl carbon and now draw the phenylhydrazine. Phenylhydrazine is H2N and here it is bonded to phenyl group. Phenyl means benzene with a free valency. So this is phenylhydrazine. Phenylhydrazine forms phenylhydrazone. Again remove the water molecule. So here you will get the product phenylhydrazone. So it is carbon double bonded to nitrogen and nitrogen is bonded to phenyl group. So this is phenylhydrazone. If the Z group is NH, there is benzene in which second and fourth position NO2 group is bonded. So the reagent is 2,4-dinitrophenylhydrazine. Now again draw the structure. So this is carbonyl carbon. When it react with 2,4-dinitrophenylhydrazine means H2N and it is bonded to phenyl group. And phenyl group is bonded to nitrogen. So here you have to number it from here. So 1, this is 2, 3 and 4. Second position nitro group is there. So NO2 group is here and on fourth position also nitro group is there. So NO2 is also on there. So the name of this reagent is 2,4-dinitrophenylhydrazine. Again remove the water molecule. So here that's how you can remove water molecule. After removing the water molecule you will get the product. This is carbon double bond. Here you have to draw rest of the structure. So this is nitrogen and here it is bonded to phenyl group. It is bonded to NO2 and here also it was bonded to NO2. So the product of this reaction is 2,4-dinitrophenylhydrazone. Reagent was hydrazine and the product is hydrazone. The last one is the semicarbazide. Amide is bonded to NH is called semicarbazide. Now draw the structure. This is carbonyl carbon, and again draw H to N, and here this is the Z group, means this is NH, C double bond O, NH2. Now again remove the water molecule, so water is removed from the molecule, and here you will get the product. See, there are 2 free valencies, double bond, and draw rest of the molecule. Nitrogen single bond NH, it is bonded to C double bond O, NH2. So this is semicarbazone. So this is the semicarbazone. It was semicarbazide and the product is semicarbazone. Now let's read from the book. Here it is written, 2,4-DNP derivatives are yellow, orange or red solids, useful for the characterization of aldehyde and ketone. To differentiate between aldehyde and ketone, 2,4-DNP test is performed. In the next video, we are going to discuss the reduction of carbonyl compounds.